Okay, now we're going to actually do the experiment. And unfortunately, it may be a little bit hard to see the vibrations, but I'm going to do the best that I can. And also try to stay within the frame of the camera. I've already done this experimentally, so I have my masses weighed out. But in the first part, we varied the tension, okay, while having a fixed frequency of 60 hertz. I've also measured out the distance. It's 1 meter exactly. So our L is a fairly easy number to use in our calculation. Dividing by 1 or multiplying by 1, there's nothing easier than that. So I'm going to turn on the signal generator. This is going to create the vibrations. And you might be able to see the string move a little bit, but it moves the most when we have a standing wave, okay? Right now, it's almost trying to do an n equals 3 here. There's a little bit of an antinode here, a little bit of an antinode here, but we're not really seeing a strong response. The longest wavelength is going to require the largest tension because the wavelength is proportional to the velocity. The velocity is proportional to the square root of the tension. So if I want a big wavelength, I need more tension. And I found that if I put, these are 100 gram masses. So I've got 200 grams on a 50 gram. So here I have a nice fundamental oscillation going on there. At 250 grams, you multiply 250 grams times the acceleration of gravity, and you get roughly about 2.5 newtons. Okay, in any case, hopefully you can see this pretty well. I will actually move this a little bit closer. Again, this is not exactly ideal, but what we can see is this antinode right at the center there, okay? So 250 grams, again, is producing this nice fundamental frequency. And I can even enhance it a little bit. Sometimes when you increase the amplitude, you get other resonances going on there too. Okay, the rattle that you hear is actually resonances within the little oscillator down here. Actually, what it's doing is it's actually a clipping, which I'm overdriving it, but you can see again, there's our nice little oscillation. So 250 grams is my first mass. It corresponds to my n equals 1. Now in the next case, I have my n equals 2. And again, there's my first antinode right there. There's my second antinode right there. And see this thing right in the center? There's an antinode right there. All right. And again, this is getting harder to see because as I go to a shorter wavelength and a higher frequency, the amplitude's not as great. I'll move this a little bit closer so you can see the oscillation a little bit better. Again, can't get the whole thing in one camera view, but there are clearly two antinodes there and a node at the center. So that was at 100 grams. Okay. Now I have this little pre-weighed one. This is, what do I have here? I have a 5 gram holder, and I have a 10. What do I have? No, I have a 20, a 10, and a 5. So there's a total of 40 grams here. I'm going to hang off the end. I'm going to take my other 0 off at 50. And now we're going to try to see that n equals 3. And here it is. Okay. Sometimes I've got to play a few games to get some of these other resonances not to be so present. But again, it's oscillating a little bit right there, but you can see that antinode there. Here's our first node at the center. I scroll over. There's my second node right there. And again, that was at a total of 40 grams. So that's my N equals 3. As I go to higher and higher frequencies, again, it becomes harder and harder to see. So hopefully you'll be able to see this N equals 4. Not great. Sort of see an antinode popping in and out here. Another antinode right here. So we need a total of 4 antinodes for N equals 4. Antinode there, antinode there. My finger's out of the thing. Antinode down here. Okay? So that is a total 5 gram holder, 10, 15. So that's a total of 20 grams on that one. Yeah, 20 grams. And then finally, my N equals 5. I have to really pump up the amplitude on this without getting it to clip. Okay, get a little bit of clipping right there. 1 node, 2 nodes, 3 nodes, 4 nodes, 5 nodes. Okay, so I found all 5 nodes, and I am ready to, first of all, turn this thing off. So I'm going to turn off my oscillator. Oh, so much better. And I'm going to come over to the computer. I'm going to see if we can get a good view of the computer screen. It's a little bit difficult because I almost have to zoom in at the same time as bring everything closer. And the lighting makes this a little bit difficult. So I'm going to close the signal generator right here. Oh, do we get any better than this? Well, hopefully, bring it closer. All right, now we can start seeing the table a little bit. I'll go a little bit at an angle. That'll actually decrease the brightness of the screen. And what you see over here is we're going to enter our 1 over n squared values. And we're going to enter our tension values right here. I'm going to cheat a little bit. And, you know, since I don't want to have to spend a lot of time doing calculations, I am going to, well, I guess I have to do the correct calculations here. I can't do 1 over n in my head for too high of an integer, but I'm going to do my best to enter the values. I'm going to pull my calculator up on my screen. Okay, so 1 over n squared is easy for the first value. That's just 1, okay? 1 over n squared for n equals 2 is 0.25, so that's not too bad. The next one is 1 over 3 squared, which is 1 over 9. It's also not too bad. That's 0.11. And then I go to 1 over 4 squared. 1 divided by 16 is 0.0625. 0.0625. Okay, so we're at n equals 4. And 1 over 5 squared is 1/25. Oh, that's not too bad. I could have done these in my head. So 1/25, of course, is 0.04. All right, so I've got those values right there. Now, if you remember, my first run, my n equals 2, I had my 50 gram holder and 2 200 gram masses sitting on top of that. So that's going to be 0.25, remember we've got to convert grams into kilograms and then multiply it by 9.8. So it's 0.25 times 9.8. All right, so that's going to be 2.45 newtons. And there's my first value. And you might be able to see it right there. The first point has shown up there. Again, I think if I do this at more of an angle, it's a little bit easier to see. I'm sort of restricted because this is on a tripod. And lower the tripod to see if I can line up just a little bit better. I need a camera person. I really do for this experiment. Okay, that's much better. Okay. Hopefully nothing falls over while I do this. But everything looks to be in focus, and you can see this pretty well. There's my first data point right there. All right, so now I'm going to do my next data point. And if you remember, that was an easy one. There I had just a 50-gram holder, and I had a 50-gram mass on that. So for that one, it's going to be 100 grams is 0.1 kilograms times 9.8 just becomes 0.98 newtons. Okay? Again, 100 grams, 0.1 kilograms, 0.1 kilograms times 9.8, 0.98 newtons. Okay, what was my next value? Well, my next value was this little 5-gram holder, and it was holding on it a 20, a 10, and a 5-gram mass. So that's pretty easy too. That comes out to 40 grams, or 0.04. So 0.04 times 9.8 is 0.392. 0.392. I'm going to put this in, and hopefully we're going to get a nice straight graph. And it's all right. It's not terrible. Let me expand this graph, by the way, because I'm only going up to a 1/n squared of 1. So my x-axis isn't going to go beyond 1. So I can expand that axis this way. And I can expand the tension up this way. Not great, okay? But, you know, I can probably fit a straight line to that with those 3 points. Okay, let's go to the next one. After that, I can't find my little mass holder. Oh, well, it's still on the contraption. Maybe if I take that off, I will be okay. And in this case, I had the 5-gram, the 10-gram, and the 5-gram. So that was 0.2. Okay. I'm sorry, it was 20 grams. 20 grams. So 0.02 times 9.8. And that gave me 1.9, sorry. Yeah, 0.196. 0.196. What happened to my value? 0.196. Okay, we entered that one. It's going okay. Looks like this first point here was not that close to where it should have been, but we'll keep going with this. And then my last point is going to be 15 grams, okay, 0.015, and we multiply that by 9.8. All right, so 0.147. Here we go, 0.147. All right, so let's expand this upward, okay? And we've got 1, 2, 3, 4, 5 different data points. So maybe the second one was a little bit off. I don't really know, but we're going to take the slope of all of those points. So hopefully, whatever we have off here, I'm going to now take a linear fit to this. Okay. And there's my slope, 2.36. And there's some variation to that. Again, I would probably say that the n equals 2 point was the one that was sort of off. And you know, the others are pretty close to a straight line, but part of the problems that we have here are we can actually get different resonances that'll shift things a little bit. But what I'm going to do is I'm going to take a picture of this. Okay, take a picture of this graph. So you'll see my iPad get in here, right here. And I'll then post that so you can see that. All right, so that's the first experiment. Again, notice over here, we're varying our n, and we're actually graphing as our independent axis 1 over n squared. That's just the way the equation goes. And we're graphing the tension necessary to get that particular type of standing wave, okay? And again, you're going to use the slope in that first equation that I gave you, okay? You're going to use that slope in the first equation I gave you. Okay, I'm going to set up the next experiment and record another video for you.